We're going to look at how negative integer values are stored in computer memory. So this is a follow-on to the video where we went over how to store a positive integer value, and we looked at number-based systems and as far as binary, decimal, hexadecimal, and decimal are concerned. Well, that covered positive integer values, but there are a lot of other different number types we'd want to store in memory. And let's start by looking at how negative integer values are stored. So to allow for both positive and negative integer values in memory, the maximum positive integer is divided in half, giving room for an equal range of positive and negative integers. If we have a 32-bit word, then the maximum number that was allowed, as we saw, was this 4,294,967,295. So if we divide that in half, that's going to give us approximately that value there, 2,147,483,647. Then we can represent numbers that go up to that point in positive as positive numbers, and about the same if we go down to negative values. So that gives us then a range of plus 2 billion and something down to negative 2 billion and something. As an example of how this is done, let's just look at a very tiny 3-bit computer in this table. So if we take our string of binary bits, we can go 000 all the way up to 111. But we want to have half of those represent positive numbers and half negative values. So let's do it like this. Okay, 0, 001, 010, 011. Let's let those represent a decimal value 0, 1, 2, 3, as we've done so far. But we want the other half to represent negative values. So if we have 100, 101, 110, and 111 left, then we can let that represent negative numbers. So for example, the bottom one, 111, would be minus 3, 110 minus 2, 101 minus 1, and 100 could be minus 0. But we don't need a minus 0 and a positive 0. 0 is 0. So what we end up doing with this 100 is we want to let that represent a negative 4. So we have taken our bits, our 3 bits, which normally go 0 to 7, and we've designated half of those to be positive and half to be negative. Now, if you notice in the negative number, and all the negative numbers, that far left bit is always a 1. So that might give you a hint as to how you can easily tell if a number is positive or negative. So that leftmost or highest ordered bit, when it's a 1, then that usually means that this is going to be a negative number. Now, if we are going to break up our bits and have half as positive and half as negative, then the range of numbers that we have is going to be a negative 2 to the n minus 1 all the way up to a positive 2 to the n minus 1 as the exponent minus 1 down here. All right? Now, if we had 32 bits, then you can see the range is going to go negative 2 billion and something up to positive 2 billion and something. So that's just a technique that was adopted in order to allow us to store negative numbers and positive numbers using the same number of bits. There are actually 3 techniques at least that can be used to store negative numbers. So let's look at those. They are called the sign and the magnitude, the 1's complement form, and the 2's complement form. So I'm going to explain each of these. With the sign and magnitude, if that highest ordered bit is a 1, then that indicates that the entire number is going to be negative. So we have designated this highest order bit as a special symbol or a special flag that means either a positive number or a negative number. If it's 0, then the rest of the word, the rest of the 31 bits, is going to be a positive number, and if that's a 1, everything else in this area, the 31 bits, will be a negative number. Let's look at an example here. Let's just take an 8-bit value. Here is the positive 7. Okay, so 0000111, that's equivalent to a positive 7 in decimal. And negative if we want to put a negative 7 using sign and magnitude, then we designate the leftmost bit as a sign bit, and we make that 1. Everything else then would be used for the remainder of the number, so that would be a -7 in sign and magnitude form. Now, this is kind of an old-fashioned way. We don't really use the sign and magnitude anymore, but it was one of the early ways in which negative numbers were designated in a computer memory. The next evolution of that would be the ones complement. So that's another method for negative integers, and it's known as ones complement. And in ones complement, the negative value for a number is obtained by writing down the positive number and then reversing all the bits. So we replace the zeros with ones and the ones by zeros. And let's use our example of positive 7 again. So here we have positive 7 and the bit string for that. If we want to use a ones complement format to do a negative 7, then we switch all the zeros and ones. So now a negative 7 in ones complement would be represented like this. Note the left order bit is also a 1 in this case. You may wonder, why on earth would we do something like that? The circuitry of the arithmetic logic unit, that brain of your computer, within the CPU is made up of electronic devices known as gates, and they implement calculations at a primitive level. So their circuitry, the circuitry would be more complicated if either the sign and magnitude or the ones complement were used. So that's really the bottom line here. The ones complement and the sign and magnitude require more complicated circuitry in your CPU than this twos complement example that I'm about to go over. So the twos complement is simpler, and operations can be performed quicker if we use this notation for negative numbers. Now, what is twos complement? It is simply the ones complement plus 1. Let's use our example of 8 bits and positive 7 again. So let's take the ones complement form. So that's the ones complement of the 7. We swap the ones and the zeros. To get twos complement, we just add 1. So if you do the binary addition, 1 plus 0 is just going to give you 1. So there, that bit string represents a negative 7 in twos complement. Well, let's look at an example to see why this is a neat way to do it. Let's add. We're going to add in binary. So we're going to add 7 and 4 using our 8-bit example. So here's positive 7, here's positive 4. Now when we add those together, just watch what I'm doing here. Okay, 1 plus 0 is 1. So we write down the 1. Okay, 1 plus 0 is 1. Then we have 1 plus 1, and in binary, we don't have a 2. We have ones and zeros. So 1 plus 1 is 0 with a carry. Okay, so this 1 comes from carrying the 1 plus 1. Okay, 1 plus 1 is 0 with a carry. So that's why we get the 1 right here. Then 0 plus 0 all the way out is 0. So when we add 7 and 4 in binary, we get that bit string, and that is equivalent to 11, and that's not binary, that's a decimal 11. What if we want to subtract? Well, if we want to subtract 4 from 7, then we start with our positive 4. We have to convert it to a twos complement form. So we'll take the ones complement of 4, we'll add 1, and we get this. Okay, 1 plus 1, that's 0 with a carry. So 1 plus our carry is 0 with another carry over here. So then 0 plus 1 is 1, and then everything else is 1 all the way out. So that's the twos complement version of negative 4. Now, let's add them. Here's positive 7, and here is our negative 4. And I've lost the solution down here. So let me modify this a little bit. Let's remove some space so we can see all that on the same page. Okay, so back to this. Okay, positive 7, negative 4. Let's add them. 1 plus 0 is 1. Okay, 1 plus 0 is 1. Now we have 1 plus 1 is 0, and we have a carry that goes over here. Okay, so 1 plus 1 is 0, and then we have another carry that goes over there. And this continues until we go all the way off to the left-hand side. Now, when we run out of bits, we just discard the carry. We stop doing the carry. So we end up with this bit string, and you know that is plus 3. So plus 7 minus 4 in 2's complement gives us 3, which is correct. What is the advantage? When we added two positive numbers, we just added them as I demonstrated earlier. We just add them together. There is a set of circuitry in your computer called an adder that adds two bit strings together. If we express negative numbers as 2's complement, we can use that same circuitry to subtract. So that's why 2's complement is so important. We don't have to write or build a subtractor to go into the computer, into the CPU. We can use an adder to do addition and to do subtraction. We just have to represent the negative numbers in this fashion. So isn't that clever? Now, we have looked then at how to handle negative numbers. What about real numbers? We've looked at how to handle, I should say, negative integers and positive integers. But also we have floats and we have doubles and we have other things. So let's just look briefly at how that's done, and I won't go into real detail here. But why are they called floating point numbers anyway? So real numbers are numbers that have a whole part and they have a fractional part separated by a decimal point, like 45.2 or 1287.6743. Those are real numbers. They can be represented as in scientific notation as 4.52 times 10 to the first and 1.28 so on times 10 to the 3. And written in terms of our C++ code, we use e for the exponent instead of having 10 there. So we have 4.52 or 1.28. Now, with these two numbers, look at the decimal point. In the case of 45.2, we move it over between the 4 and the 5. In the case of 1287.6743, we move it over between the 1 and the 2. That's why it's called a floating point. We always want to take our real numbers and have one digit followed by a dot and then the rest of the number and a power of 10. Okay, so 1.2876743 e to the plus 3. So this decimal point, it kind of floats around depending on how big the number is. The way that floating point values are represented in memory is really up to several standards. Different manufacturers adhere to different standards, but there is a small set of standards that everybody has to adhere to. Here is a very simple representation of that. With 32 bits, one of those bits is the sign bit. So we saw that come up a while ago with sign and magnitude. So with real numbers, with floats and doubles, that leftmost bit is going to designate the sign. So we're going to keep it in this case. If it's a 1, we have a negative number. If it's a 0, we have a positive number. Then we have a certain number of bits are set aside. In this case, we're showing 8. Right? So we have a certain number of bits to represent the exponent, that is the power of 2 or the power of 10. Then the remaining bits represent the number itself. So if we have a 32-bit word, then we're going to use 9 bits to represent the sign and the exponent. So that leaves us then with just 23 bits left for the number. So the maximum value then that we can store is 2 to the 23 minus 1, or a number of that size, 8,388,607. But remember that that is just a number that can be multiplied by some power of 10. The exponent can range from 10 to the minus 38 all the way up to 10 to the plus 38. So you have a tremendous range of powers that you can go through here, but you can only have 7 accurate digits for the number. So that's the important thing to remember, is how is the accuracy portrayed? What is the precision that you have? So the exponents, once again, wide range of exponents available, but you have 7 digits of precision. Let's look at one more. Let's look at 64 bits. 64 bits is a regular double type in C++. So in this case, we have a lot more bits that we can use. The left-hand bit is still a sign bit, 0 positive, 1 negative. We have more bits for the exponent. We have 11, and we have more bits to put the number in, the fractional part. So in this case, we have 11, 12 bits, leaving us with 52 bits for the number. Okay, so that's quite a bit larger. 2 to the 52 minus 1 is the biggest number we can put in there, and that is 2 to the 52 minus 1 shown here. Once again, the important thing is the number of precision, the number of digits we have. So we have 3, 6, 9, 12, 13, 14, 15. We have a total of 16 numbers that we can put in here accurately. So that is the maximum accuracy. So compared to a float, we have twice the accuracy in a double. The exponent can also be much larger. Since we have 11 bits for the exponent, then we can go from 10 to the minus 308 all the way up to 10 to the positive 308. So that's a tremendous range of numbers that you can represent. But remember, the accuracy may be what's important to you, and 16 digits would be the most accurate, the most precision you would have for a double. There are other ways to store data, and different systems may store it in different ways. In some cases, you can have a long double. Okay, so not just a double in C++, but you have a long double. So that gives you even more bits, and you can store this range of exponents here, which is just unbelievably huge. And you can have a precision then of about 20 digits. Now, that then covers how real numbers are stored in computer memory. The other type of information that's still out there is what we call alphabetic or ASCII characters, letters and symbols and things that are not numbers. There's a special code for that, and I just said it, and it's ASCII, and that's the American Standard Code for Scientific Interchange. And you can find an ASCII table just by Googling it, and you can see what the codes are. And regular extended ASCII notation, you have a total of 256 symbols that you can represent. Let's look at just one here. We're looking to store the word bird in uppercase, B-I-R-D. There's a number associated with each letter, with each number, with all punctuation and special symbols on the keyboard. Letter B has a decimal code of 66, and that is also shown here in octal, in hex, and in binary. Okay, the letter I, uppercase I, it has a decimal value code of 73. And R has its code of 82, D has its code of 68. So if you want to store this word in memory, then you would look up the number that corresponds to each letter. And then if you wanted to write the decimal out, you can, but remember, it is the binary that's stored. Always binary, ones and zeros. That's the only thing we can store in computer memory. So that would be the binary representation for those four letters, B, I, R, and D. But you can tell already it's hard to remember that bit string. It is easier to remember 68. It's easy to remember, hey, D is a 68, okay? And if B is 66, A is 65, so it's much easier to do that. So if you want to store information that is not a number, then this is one way you can do it. This example here just shows you some other information that's stored. So in this case, I've got RA34Z minus and then a left paren and a $sign, some stuff in here. So all these things have ASCII codes. Excuse me, all these things have ASCII codes. So we just stored them into memory, and we can only store 4 of them in one word, one 32-bit word. That's because it takes 8 bits to represent any symbol in ASCII. Then the number 0 to 256, that requires 8 bits to store. If we have a long string like this, then we have to break them up into groups of 4 to see how they're stored in memory. Okay, so the RA34 would be stored in one word. Then the Z minus parentheses 0, that would continue into the next set of 4-byte locations in memory, or the second word, and on and on and on. So if you have a string of ASCII information, it's going to require several words of storage and maybe lots of words of storage in your computer to store everything. So they're not bound by the 32 bits that we've looked at in floating point numbers and in integer values. Now the last thing I want to show you here is that if we have an ASCII encoded value, it's different than a numeric value. So here is the number 27, and that's in decimal. If you wanted to store that as a positive integer value, then here is the bit string for that. If we instead have a quote 27 quote, then that means that this is a string, and the numbers or symbols or letters are all going to be encoded when you have a string. So we have the we have the code for a 2, which is in binary, this string here. That's the ASCII coded value 2. Then we have the ASCII coded value for 7. So with a string, we have ASCII encoded information that's stored in memory. Whereas if we have an integer value, we just have whatever binary equivalent that is that represents a decimal value. So it's don't get those confused. Well, this video then has gone through how we can store information in computer memory. And we've looked at how to store negative integer values, and we've looked at how to store both positive and negative floating point and double values. And then we have kind of terminated here by looking at how we can store things that are not numbers using the ASCII encoded codes that go with each of these symbols. There. So I think that that's a pretty good place to stop. So we will stop the video here.